Hello everyone, welcome to this video. My name is Amir Senahrari. I am a Google Earth Engine expert. In this tutorial, I'm going to show you how to monitor one of the air pollution variables, carbon monoxide, using Sentinel-5 images in the Google Earth Engine platform. I'm going to show you how carbon monoxide changes during the time and also how we can monitor the relationship between carbon monoxide and also the energy consumption over the urban area. I'm going to show you how to do this process with the simple process that is possible in the Google Earth Engine platform. Let's go to the code editor environment in the Google Earth Engine. So, in the first step, you need to define your region of the interest. As we are going to work in urban area, it is important to select an urban region for your study. And also, all of the data I'm using in this tutorial available in all around the world freely and publicly. And also, you can use this tutorial for everywhere that you want or you want to do a study. So, for example, I'm gonna do my study actually in the region in my own country, Iran. The capital of Iran is the Tehran, and also I'm gonna focus on this region as a big city to monitor the carbon monoxide using Sentinel-5 data and also the energy consumption using VIRS satellite data. So, how we can select our region of interest? As you saw in my previous tutorial in my YouTube channel, we can use different strategies to define the region of the interest. One of the simplest one is using drawing tools available here, and also another method is using some sort of FOO administrative borders available in the Earth Engine platform. So, for example, I'm going to use province layer using FOO dataset in the Earth Engine to select my region of interest. So, here, through the search places and dataset, type FOO administrative border layers. As you can see, 3 levels available: country boundaries, first level, and second level. In this tutorial, we have focused on the first level. It is something like province borders, most likely. So, import it into the code, and you can have it as a table into the JavaScript environment. So, in order to see what is included in the table, use map.addLayer to visualize the border of the regions that table provided. Map.addLayer for the table. Write the code, and then you can see the province borders according to the 2015 available for all around the world. And I'm gonna use Tehran province for this tutorial. So, in the next step, we need to clip this region or separate it from the other borders or the other layers or other regions available in this product. It's very simple, just you need to make a new variable as region of interest. Let me to make the code a little bigger to show you better and make better understanding about the code that I'm writing here. So, ROI equals from table that filter bounds filters the layer that is matched with my study area. How I can select my study area? It's very simple. You can use the drawing tools. Using a marker, I'm selecting the region of the interest, and then based on the marker, I can select the province that I want to study. So here, filter bounds based on the geometry. because the geometry or marker is the geometry that I have created in a specific latitude and longitude. This is longitude and this is latitude. Again, map.add layer show us the new region of interest that is selected. So, in order to make a simplification for the region of interest and increase the speed of processing in the Earth Engine platform, you can use simplification order or functions in the Earth Engine. Here, as it is a feature collection, now we should make a new function to apply simplification function or simplify function on each available records or on each available region. Each input feature in the function called as a feature, and then the function returning the simplify borders. The input is feature, the input feature dot simplify based on a degree. For example, 1000 degree. 1000 degrees is a threshold I need to do simplification based on. So then run the code, and now you can see the simplified order. As you can see, in the borders, actually complexities or number of vertices clearly decreased, that helping us to increase the speed of processing. If you want to keep the order really close to the original version, you can use, for example, lower number of degrees for the simplification. For example, I can use 500 to have a better order, but still with the simplified structure. It totally depends up to you how to use and also which degree values used to do simplification process. So let's go to the next step. Then through the map.add layer, through the map.center object, we can have focus on the region of the interest whenever the code is running. So, for example, if I am in another region, once the code is running, you can see that we can have focus on the study area because of the center objects. So, for the next step, we need to call the Sentinel-5 carbon monoxide product in the Earth Engine platform. As you can see, as you know, the Sentinel-5 is one of the famous and well-known satellite missions to monitor air pollution variables, and one of these variables is carbon monoxide. So inside the box, type Sentinel-5, and here you can see that different variables related to the air pollution listed briefly. But now I'm gonna work with carbon monoxide. That's why I'm writing carbon monoxide. Two products available, offline and near real time. Would be better to use near real time products because they are provided the most recent data that is taken by the satellite sensor and is available for the users, and you can have more updated information using near real-time data. Imported into the code and now imported as an image collection. I'm gonna monitor the carbon monoxide values or the average of carbon monoxide in the province that I have selected, and I want to see that how it changes from the years satellite data is available to now. If you go to the data description, here you can see that this product is available since 2018, and also every 2 days or daily, depends on the region of the interest, carbon monoxide product is available, and also you can have actually consistent and consecutive process for the carbon monoxide in the Earth Engine platform. So in the bands, you can see the different bands or the different information available from this satellite. Here mentioned, spatial resolution is 1 kilometer, but it's a little rough estimation because when you visualize the data, you will see the lower spatial resolution. But still, for the air pollution studies, it's very low. So let's go to the process in the Earth Engine code editor environment. The target band is CO column number density, that vertically integrated carbon monoxide column density, and based on the region of based on this range of value, and also the units is available. Most of users asking about the units of variables and the measurements, but the simple question is that in the data description you can find all the information related to the every data you are using in the Earth Engine platform. So close the page and make a new variable as CO carbon monoxide equals to image collection, imported image collection assigned to the CO variable. So I'm gonna call image collections or Sentinel-5 images since the since the start of 2019. So here that filter date, I need two variables, one time start and one time end. What is time start and time end? When actually the data starting to actually the start date and time start date and or time start or time end, showing the time period in which the satellite data is taken by the satellite. So here I'm making two new variables in this regard because now time start and time end are unknown. So a new variable time start equals to 2019 and time end, as I'm producing this tutorial in 2024, I'm gonna call all the data for 2019, 20, 21, 22 and 23. That's why the time end should be 2024 here. So for the next step, we need to set a filter bound for this data. That filter bounds our satellite data, calling data for the specific region we are working for Tehran in this tutorial. So as there are various bands in this product, we need to find the target band, that here is carbon monoxide column number density. It's very simple, copy and paste it. As you may know, .select is a function allowing to select the target band easily. So .select, the target band is here. And you can set a new name by the brackets in the select. The first bracket showing the original name and the second shows the new name, CO, carbon monoxide. It's very simple and also easy to use for the next step in our programming steps. So this data is available with the daily temporal resolution, and also it is very good to continuous monitoring air pollution over the urban areas. So but I want to make a monthly format for the carbon monoxide because I need to see the temporal patterns, existing temporal patterns in the carbon monoxide in the monthly scale and also in the seasonal format to see that is there any specific pattern in the carbon monoxide in our data or not. So it's very simple technique. Now we need to make two lists. One list for the years available and one list for the months we have for each year. So here we have years list. We need to have a years list equals to earthengine.list.sequence. So list of sequence starting from the time start and ending to time end. But the problem is time start and time end are a string. They have a string format, but in the list structure we need to have the number format. So to do this, earthengine.number.parse is a function helping to convert the values from a string to the number format. Here we have time start and then earthengine.number.parse. Here we have time end. So make a print from the year.list, years, the S missed in the name. So in the right panel under console tab, you can see the period of time in which we need to make monthly data. As you can see, the time end is 2024, but as you know, in the Earth Engine, the main value of time end not included in the processing. When you set 2024 as a time end, meaning that you need to call all the data by the end of 2023, but 2024 not included for the further processing. So to solve this issue, to remove 2024, there is a simple technique, subtraction. Subtract from 1. When you run the code, here time end subtracted from 1, you can see that the list is updated according to the period of time we need. So now after years list, we need to have a months list too. New variable months list equals to earthengine.list.sequence. So the start is 1 and the end is 12. Why? Because for each year we have 12 months, and now I'm making a list with 12 records. Print months list to have better understanding. As you can see, I have a list starting from 1 and ending to 12. That's representing the pattern and the number of the months that we have for each year. So now we need to make a function. We need to make a function to return the monthly average for carbon monoxide from 2019 to 2024. Save your code and then continue coding. A new variable is made. This is CO monthly equals to first the years list. Get the years list first, then make a loop for each years available in the years list. Make a function to process based on the input. The function means that we want to do some sort of calculations for each years available in the years list. So the input is year. Each value in the years list actually called as a year here in the function. So in the body format, in the body structure, the first function returning the months list we already defined here, that's used in another loop structure. Actually here I am making two loops, 1, 2 loops one after another. In the first loop, we have the years, and then for each year, we have months. For each input month, that is called as month, we want to do some sort of processing. What is the target processing here? The target processing is filter all CO images for each month and calculate their average and also return it as a final result. Make a new variable as image in the body session, in the body part, equals to, so the CO images, including all carbon monoxide images for each date with the daily format. Now I need to filter them based on the year and also the months. CO.filter EarthEngine.filter.calendar range, one of the most valuable functions in the Earth Engine platform, and that's allowing us to do the temporal analysis easily and actively. So the calendar range, including three main arguments: the start date, the start, end, and field. You can add different fields here. For example, if you go to the docs in the left panel, in the docs, you can search about the calendar range. As you can see, in the calendar range, there is a description and also there is a lot of information about the field. What you can set for the field. Year, month, you can filter your data based on year, based on month, and based on different characters available here. I'm gonna use year and month. For each input year, I want to filter the data. The CO images first filtered based on the years list. Start and end is the input year from the years list, and the field turn to year, and then we need another filter here. The filter EarthEngine.filter.calendar range, but this time in each year we need to filter our data based on the months available in the months list. Start and end equals to each month, and the field here should be month. Finally, after filtration, now we need to get average for each month of a year. That's mean helping us to get the average value easily. So now in the next step, as we are making a new image with monthly format, we need to have a new system time start for each new image that is created. So to do this, make a new variable as date equals to, so EarthEngine.date.fromYMD. Now we can define a new system time start using this function. The year equals to the year value, the months equals to the month value, but the day is not important. You can set number 1 and remove the rest of arguments. So the function returning the average image, the average monthly image with a new system time start. As you may know, the system time start is the most important properties for the image collection, because in the next step, for each temporal analysis, we need to use system time start to justify the date acquisition or the date of the date of each image for the further analysis. That's set system time start and equals to the date. But the date format here is based on the year, month, and day. But we need to convert it from this format to another one. The another format is millisecond, because the Earth engine and JavaScript analyze the temporal information based on the millisecond format. Dot millisecond. There is. So now we need to see the output of this function. Print CO monthly. A new list is under computing. We have 5 elements. What is the problem? We have about 4 or 5 years, but here we only have 5 elements. But in each element, 12 sub-elements available. Can you see? We have 5 years, 2019, 19, 20, 21, 22, and 23. Meaning that we have 5 years and now function returning 5 nested list. Nested list is this format. We have a list in which there are sublists. So in each sublist we have different images. As this is a list format, we need to convert it to an image collection. But before then, we need to make a single list instead of the nested one. How? Using .flatten. .flatten is a function that helping us to integrate all the nested lists into a single one. Now we have 60 elements, meaning that a single list that all images available based on. So there it is. And then we need to convert this list from the list structure to the image collection structure. It is also very simple. In the CO monthly, Earth engine .image collection helping me to do this process easily without any challenge. Run the code again. Now we have one image collection with 60 elements, including monthly carbon monoxide, and for each month we have one CO image with a new system time start. That's awesome. So in the next step, I need to visualize the monthly CO images created here. So map.addLayer is a popular function for the visualization process in the Earth engine. Map.addLayer, various arguments here. Earth engine objects replaced with carbon monoxide monthly. So as this is an image collection, we need to make an average to make a unique or single image for the visualization. And then I want to clip it based on the region of the interest I'm working. Visualization parameters, no need, and leave it to empty. You can adjust the visualization parameters in the next step in the layer setting. The name of the layer you want to show is CO mean, the average image, because in the visualization process we need to have an overview or have a quick look on the data. And the shown, meaning that are you going to show the result immediately or no? You want to choose when the output shows. True and false. But here I set false because I want to check whenever is possible, whenever is needed for the visualization. Run the code. in the layer setting, you can see that the false helping me to avoid from automatic visualization. So now after code runs, click on the average carbon monoxide and I'm waiting for visualization. As this is a black image and you can't see anything, I suggest you to use a stretching technique to enhance the contrast for the outputs. In the layer settings, here you can increase the contrast by different stretching technique. I'm stretching to 90% and you can see the range of values. Click on apply and here you go. You can see the carbon monoxide image that shows and that is including a grayscale visual characteristic from the black region to the white region. The black region or darker pixels, lower carbon monoxide, and the brighter pixels or white pixels returning and showing the higher carbon monoxide. Here there is a hotspot. This is equals to the center of the area I'm working on. Here we have Tehran city, a metropolitan, a big area with 15 million people population that shows actually the high concentration of carbon monoxide, one of the air pollutions, because of the high energy consumption and also the amount of fossil fuels and also lots of other things. You can see that we have higher carbon monoxide in this region. That is typical over the urban regions. When you use the carbon monoxide image for all around the world, definitely over the urban areas, specifically the biggest one, you will see more concentration of the carbon monoxide. As we mentioned earlier, in the Earth engine, there are information that showing that the spatial resolution for this product is 1 kilometer. In the earlier stage in this tutorial, I showed you in the data description mentioned in the bands, the spatial resolution is 1 kilometer or 1000 meter. But it doesn't make sense because what you are watching here showing coarser spatial resolution. It is around 5 kilometer spatial resolution. 7 kilometer spatial resolution. But it is still good for the air pollution studies because if you go to the Giovanni websites, various actually air pollution products available there. But if you want to do the multi-temporal analysis using that data, all of them suffering from very coarse spatial resolution above 10 kilometer. In the best situation, their spatial resolution is about 20 or 15 or even 10 kilometer. But this is 7 kilometer, and also it is a good option for the air pollution studies. So, and after you get insight about the data characteristic and the data conversion and visual characteristic, in the next step, I'm gonna show you how to monitor the changes, the carbon monoxide changes over the urban area. So, in the first step, in the province scale, you saw that how we can find the hotspot for the carbon monoxide. In the next step, we want to see that how the hotspot changes during the months and even season. It is very simple technique. You can select the hotspot or the region using the rectangle or polygon available here. So here I'm making a new rectangle. First, remove the previous one, and using the rectangle tools, I'm selecting the point that is related to the hotspot. So after this process, we need to use image.series function to monitor carbon monoxide changes from one time to another. Print user interface chart image.series. Image collection replaced with CO monthly, and then the region in which we need to see the patterns of carbon monoxide equals to the geometry as a rectangle, and I want to have the average value using the reducer earth-engine.reducer.mean. I can get the average of carbon monoxide over the selected region in the hotspot. And the scale is 7,000 meter because the real spatial resolution is 7 kilometer. And X property equals to the system time start. As you can see, previously we made a system time start because we need it. We need it for the next steps. That is here. A new chart is under generation. This chart, as you can see, shows the temporal pattern of the carbon monoxide from the early 2019 to the late of 2023. There are some ups and downs. As you can see, in the winter time, January, December, January, November, December, January, and again December, you can see we have higher values. And in the warm seasons, May, June, July, and August, you can see the lower values. So meaning that the carbon monoxide changing from one month to another time. We can conclude that the carbon monoxide has higher value, tends to higher value in the winter time because of more energy consumption, and also in the warmer time or warmer season tends to lower values because of the lower energy consumption. How we can monitor the energy consumption here? One of the best products that I can show you here using satellite data is a nightlight product. The nightlight product showing that how the electromagnetic shows the rate of electricity consumption or the electricity radiance emitted from the urban area in the night time. This product is also very useful for the urban monitoring. But another application of this product is about the monitoring of energy consumption. When the electrical radiance increases, meaning the higher energy consumed. So how we can do this? It is very simple. In the box we have write about the Beers Nightlight product. Beers Nightlight data. So Beers Nightlight. No result with a space try. So Beers land daily corrected straight light. Yes, we have different products in this regard, but we can go to the browse data to see that how actually nightlight product changes, and also what kind of nightlight data available for us in the Earth Engine platform. Through the browse by dataset tags, type about the night time. Go to the nighttime tags and you can see various Beers products available. One of them is Beers Nighttime or day or night band composite version 1 that's showing the average radiance with 500 meter spatial resolution. That is very good for the energy consumption detection here. So it has monthly format because in the collection snippet clearly mentioned its temporal frequency. So just we need to copy the collection snippet from the here and paste it into the code. A new variable as, for example, light equals to the new image collection we have. Then we need to set a filter date. This product is available since 2013 or 12, and also we can have for the same date that carbon monoxide data is available. And no need to do temporal conversion because it already has or including the monthly data. Filter date equals to the time start and time end. Time start and time end. And what about the target band? The target band is the average radiance. Copy the name and paste it here. There it is. So for the next step, we need to plot the variations of the night light for the region of interest. But before then, I want to make a visual. I want to visualize the night light data to see how the night light data works and makes better understanding for you for the next step. In the Earth engine, when you want to do the process, you need to have a background about the data. If you cannot imagine what kind of data you are working, definitely it will have a negative impact on your estimations because you cannot imagine what's going on there. So before imagine, we need to have an insight or background. It's very simple. Map.add layer. Thanks to the Google Earth Engine, everything is available with the simple scripts, and you can avoid from very complicated programming and boring techniques that is not related to the field of studies we are working. Just we need to have data, do some process and extract information, interpret the results, and also do our research. Light data replaced here, and also now we have light average. Run the code. This time we have average electricity value. So in order to have a better visualization, go to the layer setting and increase the contrast by 90% stretching technique. Now you have a better and reasonable output. This is 500 meter. If you want to have more information or clearer information, you can increase the stretching technique. As you can see, the night light data reflecting the electricity or the lights emitted from the residential areas. As I mentioned earlier, here the Tehran is one of the biggest cities in all around the world, and also it is a metropolitan, and you can see the distribution of this city in the main area and also the surrounded region. The grayscale image we have here, including two different colors, black and white. The white region showing the electricity emission from the lights or from the lights that are emitting the visible light during the night, meaning that the energy is consuming in this region. So, because somebody living and somebody using. For example, here there are some roads from the Tehran to the south and to the north and to the south, that you can see the lights reflect the lights in the air in the actually streets and also in the roads, reflecting the visible energy and detected by the satellite. That's why you can see the small settlements and also residential areas and roads. everywhere that energy is consuming. So now we want to have a monitor, we want to do monitoring for the hottest spot. The hottest spot we detected located to this region, and now we want to monitor the variations of the energy consumption in this region. Even we can increase or expand the region of interest, because here we have higher spatial resolution, and definitely we can get more information about the energy consumption, and we can have a clearer view for the defining the region of the interest. So use the same code as print we had before, but this time for the light data. Replaced with light, and also the spatial resolution here is 500 meter. And to separate two charts from each other, we can add some options to each. Here for the first one, that set options is a function allowing me to add some parameters for the chart. One of them is the title. The first chart reflecting the carbon monoxide or CO. And also the vertical axis showing the CO values. Here we have vertical axis equals to, there is a title, it is CO, or even we can add the unit of the value, mole per square meter. For the horizontal axis that's showing the date, horizontal axis equals to a new title, the date. And also we can set a color for this plot to make it separable, to able to distinguish the first and second one from each other. So from the series, the first chart or the first plot change its color from the current color to the red. And if you want to add some points for each date, point size is a useful parameter. Point size equals to 4, for example. So here it is. I can repeat or use the set options again for the second plot. But this time we have electricity consumption, a new name, and the title for the vertical axis is a radiance, the amount of visible energy reflecting or wavelength, amount of visible electromagnetic radiations that's coming from the urban area. It is a radiance means in this product. And also the horizontal is date axis, and also the color could be orange. I think it's good. Save your code first and run it again. Waiting to get the charts. So as you can see, we have a chart that's showing the as you can see here, that's showing the variations of the carbon monoxide and the values of energy consumption. So for some dates, as you can see here, we have the no data value that's highly affects on the quality of estimations, that we need to exclude these months from the processing to avoid from some sort of problems that may occur in our understanding about the output. How to do this? We can do this by a new function. For example, here I can make a new function EarthEngine.filter.calendar range. The months that the data missed is related to the June and July. So the months number 5, 6, and 7. The months, if we convert it from to exclude this time, this months from the estimations, we can use .not. But unfortunately, .not doesn't work here. Let's try with another method. I made a little change and I hope the problem is solved. Yes. Now the problem is solved. Using .not, we removed the months we had problem. As you can see, there are some ups and downs in the electricity consumptions. As you can see, in the winter time, all the peaks related to the cold months, and in the March, in the January, in the February, and also during this time, we have higher electricity consumption, higher energy consumed in the urban area, and also it is anticipated higher carbon monoxide for the region of interest. If you want to download each one of these plots, just go to the data and click on the download CSV. You can have access to the CSV format for the further studies. So, in this tutorial, I showed you how to use Sentinel-5 data for the carbon monoxide monitoring and how to assess the electricity consumption. Although the energy consumption not only related to the visible or light energy reflecting from the urban area, but it is an indirect estimation that's showing a part of electromagnetic radiation that is consuming by the urban area during the different times. And I hope you got a good insight about the air pollution and its variation over the urban area for carbon monoxide. If you had any problem regarding the code, I suggest you in the first step compare yours with mine. But the code is also available below the video description in my YouTube channel, and then if a still problem exists, you can reach me out through the YouTube channel and put your comments. I will be happy to check and answer. Thank you for your attention.